This is a video about dimensional analysis and astrotometry and the notion of cause and effect and the implications that hypertime and the indications of the hypertime shadows have on our common notions of what cause and effect actually is. And I took another look at Rob Bryanton's book, Imagining the 10th Dimension. I didn't realize that when I had opened it previously that I'd opened it to the second to the last page of the regular part of the book. There's an additional part of the book that is an afterword and something on interference and connections, and then a bunch of songs that Rob wrote about things that are related to life-changing things. And I'm going to reorient my videos towards the people in the front row, the people who have seen that the universe is not exactly what we thought it was, and who are interested in sorting out the details of the new and emerging paradigms on the construction of the cosmos. In the common notion of what a dimension is in mathematics, a dimension is a measurement of something. When something has a dimension, it has a scalar quantity that's associated with it that is its dimension. In other words, if you have a ball, for example, this ball might have a diameter, and this diameter is a particular quantity, and that is a dimension in mathematical analysis. Now, the word dimension has been used in several different ways to extend the concept of what a dimension is. The word dimension has been used metaphorically to talk about something that has a particular aspect or a particular angle. And then some mathematicians are a lot more strict with their definition of dimension. Now, in astrotometry, I fall on the stricter side, but I try to avoid the word dimension altogether. And I understand that it's a useful word, it's a very useful word, especially for abstracting. And while imagining the 10th dimension is a more abstract way to imagine things, the astrometric analysis is a more tangible way of looking at things. So if you have, for example, now I'm paraphrasing, I'm not sure that this is actually a correct interpretation of Rob Bryanton's dimensional analysis, but if you assume a universe where you have sets of three-dimensional worlds, and in computer graphics the three-dimensional world is frequently represented with these three arrows indicating that there is three-dimensional space. So in a two-dimensional drawing, you have on the board, we have this dimension and this dimension. This is a 2D board, and so as a 3D moniker for a 2D moniker for a 3D space, these arrows are frequently drawn this way. And so this would be one 3D space. And then you could say you have another 3D space. And then with a third 3D space, you get into basically 9 dimensions. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you think of these as sets, if you think of these dimensions as sets of real-world worlds, in other words, if you think about the world that we live in, if you think about the world that we exist in as being one three-dimensional world, this is a good way to represent it. And I think that this is the way that Rob does it more or less in his book. And so you've got these three-dimensional worlds here that make up the 9th dimension. And so you've got this other dimension that would be the 10th dimension that allows you to move among more than one three-dimensional world. And so you've got references of 3 3D dimensions, and that would make a 10th dimension. Now, in astrotometry, I don't apply the word dimension in the same way. When I use the word dimension, I generally, whenever there's a dimension of space, I generally leave it a constant. In other words, I don't consider these three spaces separate. I don't consider these to be separate. And I totally respect the use of the word dimension as that. It's a very useful way to abstract it. But my convention, the convention in astrotometry is slightly different, and that's why I wanted to bring this up. Because in astrotometry, you might label these X, Y, and Z. You might label these X, Y, and Z. In astrotometry, these are the dimensions. So you've got the X dimension, the Y dimension, and the Z dimension. And these X, Y, and Z, X, Y, and Z, exist in all three of these separate spaces, which can be considered separate dimensions, which is a completely valid way to analyze and work with the concept. But in astrotometry, when I say dimension, a spatial dimension, I'm only giving three, which is basically our X, Y, and Z axes. And so that's basically, you've got an axis that runs up and down, one that runs east-west, and one that runs north and south. In astrotometry, they are strictly defined that way. So when I say dimension, the X dimension runs from east to west, the Y dimension runs from north to south, and the Z dimension goes up and down strictly. Those things are strictly applied in astrotometry because of the nature of the understanding of what electromagnetism is and how it relates to these dimensions. And so in astrotometry, it's a more rigorous analysis of what these characteristics in our world actually align to in higher dimensional analysis. And so in astrotometry, there's the issue of hypertime. And in astrotometry, you could say that the three-dimensional world that we see, so if you've got, I'll make a bigger 3D world. So if you've got X, Y, and Z, X, Y, and Z. I made a mistake here. X, Y, no, that's right. X, Y, and Z. And the X, so the three-dimensional world falls out of, is created by H. We'll call it H for hypertime, because the concept is that in astrotometry, the hypertime dimension is what creates the three-dimensional world, that we see, as an interference pattern from these other dimensional worlds. And so there are multiple of these that are understood to exist in astrotometry, but the relationship between them is described in a different way. And so I'm describing the various worlds that interfere to make what would be a current world, which basically just is done by assigning a hypertime to it. A particular hypertime indicates a particular world at a particular space. And so hypertime has technically has two dimensions to it. And the two dimensions in hypertime are a spatial dimension, that is the displacement between one of these other universes. So there's a spatial dimension, which is one of those scalar quantities. So H is a spatial dimension, and then it's also, if you consider time a dimension, there's also a time associated with it, because, and so when I notate HT, that's two dimensions, the hyperspatial dimension and the time dimension. So there's a hyperspace dimension, and then there's the time dimension. And so the HT is a displacement in space and a displacement in time. Now, the displacement in time is tricky because it happens between the times. And similarly, the reason that the analysis on this is so difficult is because the three-dimensional worlds are forming and reforming, materializing and rematerializing in between the spaces and among the spaces that exist in our physical space. And so the way that I'm going to be presenting, and I just hate to do this. I don't like the mathematics. I mean, if you push me if you push me on the mathematics, what I'm going to do is I'm going to tear down the existing mathematics, because the reason that I'm not wanting to assign the mathematics is because the mathematics that we have for the heliocentric model is wrong. If you want to apply Newton's equations and you want to do a rigorous mathematical analysis of what gravity is with respect to our understanding of what the sun is, if you do an analysis of that, you find that it's not consistent, that the mathematical analysis is not consistent with the observations. And science has made a terrible, terrible mistake by sweeping these inconsistent analyses under the carpet, rather than saying, oh, these are big problems with our model that we need to figure out what a better way of looking at this is. And so I don't want to make that same mistake with astrotometry.